Yeah, hello everyone. It's my honor to introduce Florian Fischer here today to give us a talk on his research. Florian is a postdoctoral researcher at Intelligent Interactive System Group at University of Cambridge, who is working on understanding and development of efficient, ergonomic, and accessible interaction between human and digital device. Florian used Mouse Suite to build simulations and explore um, how we can build embodied visual motor models that can be used to simulate restricted human computer interactions. His work bridge biomechanics, perception, and connection to build reinforcement learning agents that behave like real-world users. The simulated user are already being used to design really good and like adaptive HCI devices, and especially in a VR and MR settings. Florian also developed the muscle fatigue model for our mouse suite communities. So it's my pleasure to have Florian here, and I will hand over to Florian to introduce his work. Yeah.
Yeah, thank you so much for the nice introduction and the opportunity to present me and my research today in this talk series. So today I'm going to talk about how we can use biomechanical simulations for HCI. And HCI, so human-computer interaction, is a quite diverse and broad field, incorporating a lot of backgrounds and also methodologies. So we have a lot of quantitative approaches in the sense of problem solving, where we observe what users need or what might go wrong with suboptimal in interaction with any kind of artifacts or systems, and then improve and iterate on these artifacts consequently. And we also have the generative approach or deductive methods where we use models from a broad range of fields and backgrounds to predict how they might affect interaction, how interaction will be affected by certain design choices and correspondingly design interfaces, interaction techniques. Biomechanics, as you might see, does not play a major role currently in this. And this is quite surprising, given that if we have a look at all these different kinds of interaction techniques, though they're really diverse, require diverse skills, they all have something in common. They're fundamentally based on human body movement. So it is surprising that in HCI we currently do not really understand how and why users move in interaction and how this affects our systems. So traditionally, we're using several models that stem from motor control. For example, Fitts law, the most prominent one, which is applied across a diverse of applications and tasks in HCI, which constitutes a linear relationship between the difficulty of a pointing or reaching task, expressed by the ratio of the distance between the 2 points that should be reached and the accuracy that is required, and the movement time that it needs to perform this task. So it has some grounding and some reference in human motor control. It's also related to the well-observed or well-established phenomena of speed-accuracy trade-off, but it's mostly used as a summary statistic to predict a discrete event, like the time when we complete a given task, for a certain setting, similar to the steering law, also the keystroke level model, a famous HCI model, which has been applied across a range of tasks. For example, here to predict based on a decomposition of a task of going to a certain menu or changing some settings on a mobile application into its subtask, and then the summation of the cognitive and execution times required for these individual components. So we do have this close relationship. However, biomechanical models themselves at the moment do not play such a large role as they could, because body movement conveys a lot of meaningful data. So it has been used and is continuously used to infer information about the user's intent in an interaction task, but also about their uncertainty or well-being in general. So, for example, this body movement data can be used to infer uncomfortable movements or straining body postures and prevent them, and also physical fatigue, a topic which I'm slightly going to present a bit more details about later. So we have some models or some approaches which make use of biomechanics or movement data for ergonomics. So one important um, project I like to point out here was proposed published a few years ago. That's the XR ergonomics toolkit, which allows designers in 3D spaces and mixed reality or VR to assess the 3D location of certain widgets or containers based on their ergonomics. So it informs them about the ergonomic cost of design based on different metrics that are implemented, based on the movement data collected and then analyzed or processed via inverse kinematics when the designers try to reach the objects on the places assigned to them. So this is very helpful and shows as a first step, the possibilities that ergonomics and biomechanical research can have on the design of UI interfaces, especially in the 3D context. However, it's limited to static poses and uses a very simple kinematic chain for this inverse kinematics. So to summarize, there is a lot of opportunity of using movement-based models for HCI. They could help to design parameters that account not only for performance, as we've seen before in models such as Fitts law, but also for the ergonomics or comfort. And in particular, it's important to mention that also performance is predicted by those models. So if we have accurate enough models, this will not limit us in anything, but we'll just be able to combine the theories and models and test for coercive predictions. And an important, as I already mentioned, important area where this might be even more useful than desktop or mobile environments is the immersive sphere, so XR interaction, where standards still need to be defined. So at the moment, there still is not such a default interaction technique or even gesture as we have with mouse pointing for desk or keyboard typing for desktop environments, for example. And by analyzing and enhancing these methods based on also physiological aspects from movement-based models, we can ensure that these standards are really set to improve user experience in a holistic way. Also, an important aspect is that movement-based models or simulations in particular have the potential to partially replace tedious or unethical user studies. So especially when we consider the broad range of abilities and also physiological constraints that users might have, that's something very difficult to test. So in terms of accessibility, designing interfaces that are not only accessible by the mean user, by a very diverse range of users, is something that requires a lot of expensive, tedious, and in some cases even unethical user studies if we require the users to test some conditions that might be very uncomfortable or hazardous. So replacing or at least complementing these user studies with a simulation-based testing approach, the so-called automated biomechanical testing in an early stage of the design process, will also open up new opportunities for better and more accessible design. And also for HCI, it will help us to generate more quantitative comparisons if we have like a benchmark of different simulated users, environments or interfaces could also be tested with. And in general, also, it will help us to reconcile and refine the broad range of coexisting HCI theories and models that we already have. So the question I want to address in this talk is how can we understand and predict how users move in interaction? So we'll propose a computational approach using computational models of movement-based interaction, which I'm going to talk about in the first part of that talk. And we'll then focus a bit on how biomechanical simulations can specifically be used for designing VR interfaces. And we'll conclude with current challenges that we are facing and where the Myosphere community might also be really beneficial in addressing those. So we first need a computational, if we want to model or create a predictive system of how users interact with a given system, we need a computational model. And this is based on the assumption of optimal feedback control. So optimal feedback control is both a mathematical framework for solving sequential time continuous control or decision problems. So has a strong foundation in control theory and mathematics in general, but had also been proposed as a theory of human motor control, closely related to the minimum intervention principle, which states that users only correct for perturbations in their movements if they interfere with the objective they have in mind, suggesting that there is something like an reward or cost function that we aim to optimize implicitly when interacting. And that's also at the core, as I will show in a second. So the basic assumptions are we have controllability. Humans are actively able to control their body via sending specific muscle signals. Then this optimality assumption, the controls are adjusted when they interfere with higher objectives. And this is done in an online manner. So we do not assume or do not have a strict separation between the planning and the execution phase, but instead can online account for disturbances or perturbations whenever we notice them. So when perceptions become available. So for the combined system of the human controller on the left-hand side and the human system interaction dynamics, like the plant consisting of the user's body and also the interface users are interacting with, this means that users continuously control this plant, this combined system through body movements. Effects can be continuously observed through feedback, and this is compared to the expected feedback internally computed based on a model we have of the environment to form a state estimate, and based on that state estimate and given our task objectives, the controls are then chosen to be optimal to satisfy under all these uncertainties and noises and the constraints imposed by the body and the environment to the extent possible. So in fact, this results in a simple constraint minimization or more common in reinforcement learning maximization problem where the question is how we can choose this control this cost function J, how this should be chosen based on the task and the environment and the interaction technique we are currently considering, and also what, depending on the purpose, needs to be included in that model in the system dynamics F and the states X. So that's basically design questions. And a few years ago, we started with applying this optimal feedback control theory for human-computer interaction. Started with the most simple and basic task, and so one-dimensional mouse pointing, where we assumed quadratic costs so we penalized the final distance, velocity, and acceleration error in that between the mouse cursor and the target, and also control costs applied at every time step. And together with a very simple linear model of these combined system dynamics, we were able to show that the predicted movement profiles exhibit very similar or are in line with well-established patterns from human motor control. For example, we have these clearly bell-shaped velocity profiles, and we're also to show some other effects that were established from literature. So it is possible to predict to some extent these movements, even for individual users, by adjusting the parameters on a per-user basis. But clearly, this is a very limited approach, because here we used the LKG, like an analytical model, which has the strong assumption of linear dynamics. And this was doable for this simple approach of small mouse cursor movements, which do not require a lot of rotations or any larger body movements that are clearly nonlinear. But to model mirror interaction in VR, we need more sophisticated methods. And also more sophisticated models, clearly. So here, the simple point mass model of second order also reaches its limits very soon when we extend the range of tasks we want to model. So the second component, in addition to that model of how users interact with a given plant, is a sophisticated biomechanical body model. And as you all know, there's a whole range of different complexity types and also scopes, whether we're only interested in kinematic, dynamic models, whatever. So here we also thought of starting with a linked segment model, but soon figured out that due to the importance of a good shoulder model, which is not possible with those simple linked segment models, this we need more advanced approaches. So we use advanced models implemented in a physics engine, Mojoko in this case, the musculoskeletal model, and we're also mainly focusing on forward simulation in line with that computational modeling approach I've shown before. So remember, for these given a task objective, which in our case does not incorporate reference data, so it's not like a tracking task, but more an optimal control task for the task objectives that we define. This can be forward simulated and predictions can be generated without any reference data, at least for the forward run. Of course, we need data in some other aspects. I'll come back to that later. So we use the mobile arms model, which is a state-of-the-art model of the upper extremity, modeling the shoulder with 3 degrees of freedom, the elbow with 2 degrees of freedom, and the wrist. It also has the torso included, but this was fixed for our purposes, and in particular, it's muscle actuated. So in previous projects, we also were able to demonstrate some kind of biomechanical plausibility and also applicability to predicting mid-air interaction tasks with a torque actuated model only. But again, here we have clear limitations of the scope and of the accuracy. So including muscles was a must have for us at some point. And this model includes all bones, muscles, tendons, and ligaments with these 7 degrees of freedom. And in theory, it has 50 muscles. For our tasks, which most of my talk will focus on, it was sufficient to mainly focus on the muscle in the shoulder and the arm. So we fixed the hand and excluded the wrist and finger muscles, reducing the still relatively high dimensional control space to only 26 muscle compartments that need to be actively controlled. And another aspect which is very important for us, I already mentioned that in the beginning, is this perception, because we assume that perception and muscle control form the basis of human-computer interaction. So to understand how a design choice affects the movements and the performance, which we can measure from the biomechanical models only, we also need to model how these changes are perceived from the user. So there's opportunity to model all the different sensory inputs we users will perceive in interaction. We've mainly focused on 2 of those. That is proprioception, so the sense of body position and states, and vision. We also currently have some projects integrating audio and also haptics, which might be important when it's about the design of vibrotactile feedback, when the VR controller vibrates or something like that, or also for other input devices is also on our list. But for now, it was mainly proprioception and vision. So the idea is to combine these different components, these types of models, into a biomechanical user simulation to produce so-called simulated users in interaction. And here, due to the high nonlinearity and the biomechanical model being implemented in Mojoko as a black box physics engine, we clearly need to rely on reinforcement learning. So the state resembles the perceptual input the user receives at every time step. So in our case, incorporates a very simple vision model. It's just the fixed field of view and RGBD array that we used initially. And then this proprioceptive information about the angle, velocity, and acceleration of the joints and the muscle activations. We could also, when it's about multi-goal, multitask learning, include other task-relevant information into that state space. And then we have an action space. That's the output the controller needs to design or needs to come up with, which is simple, the muscle control signals. Also here, for the muscle control signals, we experimented with different versions, for example, outputting either the direct muscle control signal or the relative difference to the current muscle state, so the current muscle activation, where the latter has also shown to be beneficial in terms of training efficiency. And yeah, we train this, we train a reinforcement learning model here, in this case using PPO usually, to learn this muscle control policy mapping arbitrary states, so perceptions, to these muscle control vectors. And of course, this requires for different tasks to come with different reward functions. I'll say a bit more about that in the end of my talk. But we were able to demonstrate that this results in reasonable, successful policies for a range of visual motor interaction tasks. So we started with a basic middle pointing task where the goal is to move in the fingertip inside these penetrable virtual spheres of different size and located at different positions. So we ensured that a single policy is able to reach all those targets in a quite broad range of locations and stay inside there for a certain dwell time. So this requires like 30, 40 million steps to train this muscle control model from the scratch. And it achieves a very high success rate of around 99% across these range of sizes and positions. But we also trained different policies for different tasks. For example, the similar tracking task, where the target is following random sinusoidal curves, so it's difficult to predict where it will move to, requires especially this coordination of visual input. Remember that the target position is not explicitly given as an input state, because this would, yeah, would neglect our idea of relying on perceptual visual input, particularly in this case. As well as a choice direction task as a prototype of a visual motor coordination task. So here the agent needs to learn to click as fast as possible to the button of the color that's currently shown on the display in front of them. And we were also able to demonstrate the applicability of this approach for a higher dimensional interaction task, which require multiple skills in parallel. So we modeled here interaction using an input device, such as this gamepad, which has this joysticks, and it needs to learn to use the left joystick to. So first needs to learn to control the muscles to move to that joystick, and then use that joystick to steer a remotely controlled car, this red car, inside that green target area inside that box. So that's a high dimensional control task, because we have the second order muscle activations, which produce force. We then have the movement of the joystick, and this is mapped to the acceleration of the car. So adding another two orders of control. But this can all be done with a single reward function without complex curriculum, with reinforcement learning based on the visual and proprioceptive input. And we were not only able to demonstrate that this can result in kind of successful performant movements, but also that these follow these already mentioned established movement laws. For example, if we compare the movement time generated from these simulated users for different instances of the pointing task, so different distances and target width, this is very well in line with the Fitts law, which we typically observe from real user studies. And also the closely related speed accuracy trade-off, which states that if we loosen the requirements of accuracy for the target, for example, by extending the size of the target, here the width in the left plot on the right side, this leads to higher velocity. Also, this overshooting of the target is a well-established process, because it tends more to that only ballistic phase, and then requiring smaller correction movements in contrast to movements or tasks which have higher requirements on the accuracy. So these are phenomena that hold well for the predictions generated by our model. So after these initial findings, we were interested in, well, these still are kind of toy examples where we clearly define the environments to be relatively simple, not many distractors, and also the task to focus simply on a single more or less on a single or a few movement reaching tasks. So we're interested in, can this also be useful to predict user interaction, movement-based user interaction in more complex real-world environments? And we particularly focused on virtual reality. So our goal was to integrate these biomechanical simulations into an IDE, such as in our case Unity, for VR design. And if we would use the previous approach out of the box, this would basically mean we would not only need to simulate the user, but also the environment, because it's very tedious and not very feasible to re-implement the complex graphics and visions and game logics even of an implementation in a game engine such as Unity to re-implement all these details in the physics engine where the simulated agent lives in. So if you consider a task of like Fruit Ninja where we want to predict how tedious, effortful, or performant it is to cut those different fruits popping up somewhere in mid-earth space, we'll probably rely on very simple spheres, which again reduces the ecological validity of those simulations. So in contrast, we have a completely different interaction between the real user using the headset, the VR controller, interacting with a real VR application. And we have a gap between those. And the goal was to close this. And to this end, we developed Sim2VR, which is a tool that enables simulated users to interact with exactly the same VR application that real users are interacting with. So it sees the same on this simulated head-mounted display as a real user would do, and it also can control this virtual controller. Has the same abilities to control this virtual controller. So we have a better alignment between the interaction loop in reality and the simulated one using our biomechanical approaches. So the result, just as a quick walkthrough, we have simulated user selects muscle control signals, generates body movements. This updates the position and orientation of the VR controller and the head-mounted display. And that's the data which would also be sensed by physical hardware. So we process that in very same format and send it to the VR application, which is agnostic of whether it receives simulated or true physical sensor data, and therefore also use it in the same way. So it updates the game physics and game logics. The only difference is it computes a reward signal because of our L-based training approach. So that's not necessarily doing evaluation, but for training the simulated user, which is our next goal then, once we have established or integrated the simulations into VR, we need the reward signal. And that usually depends on the score that might be given, also often shown for VR games on a scoreboard to users. So we use that. But also render the scene in the very same way and send this rendered image along with a game reward to the simulated user, closing this loop between the system and the controller. So this results in this closed feedback interaction between the simulated user in the physical space and then this virtual representation in VR. So the key components of Sim2VR are we clearly need to simulate the hardware. So that's one of the efforts we took. It was also essential to rely on a standardized VR interaction library, OpenMXR in that case, because we need to ensure that the VR application is agnostic of whether it's simulated or real input, and attaching to that library helped in that case. And of course, we need to direct access all the relevant variables, in particular the same cameras, the scores, everything that might be needed, or otherwise be passed to the real user to also ensure this alignment. And of course, the simulators, like the game engines, physics engine for simulated user, and the game engine for the virtual environment, need to be spatially and temporally synchronized. So we tested this for the Whack-A-Mole game, which you might all know, where the task is to hit those green targets that appear on one of 9 positions on the target area as fast as possible before they explode, using that virtual hammer, which can be controlled with a VR controller. And we assumed that designers might, for example, be interested in the target plane position and orientation as a design variable to control or to get more information about. So whether or how it affects the interaction, if it's placed more on our upper body position above the user in contrast to facing the user in front of them. And similarly, we also introduced difficulty conditions, basically defining the maximum number of targets that can be shown simultaneously. So therefore increasing the complexity and speed of the game logics. And we trained, again, using a very similar reward function, the simulated user to interact with this environment. Looks like this. And that's only for validation. We also conducted a user study. So we asked 18 participants to also play those different levels or variants of the game to get reference data in order to see how well our simulated user or this automated testing approach could predict insights we could have otherwise gained from a real user study. And indeed, there's a lot of similarities. So in terms of performance, for example, we were interested in the number of successfully hit targets shown in green and the number of missed targets shown in orange for the 3 different difficulty conditions. And if we only consider the left and the mid bars respectively, which come from 2 different instances of the simulated user, we see that these show similar differences between the difficulty levels as the right bars from the real user study. For example, we would have already noticed from the simulated study that increasing the task difficulty from medium to hard only increases the number of missed targets, but not necessarily the number of successfully hit targets. So there's like a performance limit, and probably users might at least not experience the hard task or value the hard task more than the medium task. Of course, there are other variables involved which cannot be directly simulated or predicted by the simulated users in terms of user experience. But this already gives good predictions of the performance differences across different design choices. And it also, of course, it's one of the benefits or one of the goals or the reasons why we want to include muscle actuated models. We can also predict the effect of different conditions on the effort. So here, both in the simulated user study, but also in the real user study, we observed that the high condition resulted in significantly higher muscle fatigue over these 1-minute episodes than the remaining 2 conditions. And maybe even more interesting, simulated users can also be used to reveal potential strategies that users might detect and exploit in practice. Also loopholes in some sense, so it depends on the intention of the designers. For example, here to test this, we implemented 2 different variants. In the constraint variant, the targets need to be hit with a minimum velocity threshold to be successfully hit and destroyed. In the unconstrained variant, this was not necessary. And when training 2 different simulated users on these 2 variants of the game, we also observed that they learned different strategies. So in the constrained variant, of course, it was needed to move the arm back between all these movements to gain enough momentum to reach this minimum velocity threshold and acquire the needed force. Whereas for the unconstrained variant, without that velocity constraint, it was possible to just more or less stay inside and slide through the targets or touch them. We also see that when we plot the hammer depths during the movements. And interestingly, though we never prompted any of the real users in the study about this possibility, some of those also identified when they interacted with the game and applied very similar strategies. So this difference between the strategies or the general movement trajectory of both the arm and also the virtual simulated objects is very similar in both cases. And of course, Sim2VR. So if you're interested, it's all open source. Feel free to apply it. Is not only applicable to our whack-a-mole game, but also to in theory all other movement-based VR games implemented in Unity. For example, we also tested it with a Beat Saber game from the Unity store. So to summarize, Sim2VR constitutes a key step towards this goal of automated biomechanical testing for the case of VR environments, as it allows researchers and designers to run these simulations directly in the same VR application that users will interact with, and to perform measures and metrics such as performance, ergonomics, and also potential user strategies. However, there's clearly a limit of the scope of tasks where we foresee this could be reasonably applied. In particular, it gets more difficult when we talk about more open-ended, creative, strategic tasks, where it's unclear how to encode this in an appropriate reward function or reinforcement learning approach. So again, here movement-based tasks with simple logic or order of required movements are the most useful or directly applicable ones here. And there are more challenges. I'd like to talk about this in the last minutes of this talk. So, of course, there are a lot of challenges. I want to outline three, which are currently limiting the way we can, or limiting the applicability of biomechanical simulations in HCI in general. So it's about the biomechanical plausibility of the models we use, but also the diversity and the ability to personalize and customize them, and then this problem of designing the reward function, which I want to talk about at the very end. So first, this biomechanical plausible models. Clearly, it's as I mentioned, we initially considered using simpler linked segment models and also experimented with biomechanical models with torque actuators only, and that's a huge increase in terms of prediction quality and plausibility by using these state-of-the-art biomechanical models originally implemented in OpenSim. But still, those were mainly, OpenSim is mainly a tool designed for inverse kinematics and dynamics, so inverse simulations where we have reference movement data and want to infer underlying parameters from this data, which makes it less important to accurately model, for example, the joint angles and some other properties of the model. And we also experience this because it's completely different reinforcement learning, where we, in contrast, even incentivize the agent to explore the possible state space, so everything within the ranges of or boundaries of the biomechanical model to the extent possible to find the best optimal strategy, where we see that often, not only during training, but also in some cases where convergence is poor, in the final output policy, behavior that is clearly not biomechanical plausible. So movements that should actually not be inside the range. For example, this one, or also here, that was an initial run for training the Beat Saber game, and that's clearly not how users would do it or could do it. So better modeling of this joint limits and verification, specifically of this arm, hand, shoulder model, which is at the core for most movement-based interaction tasks, is one requirement where more effort is needed. Also, it might be the case that the shoulder model still is a bit too simple, because clearly, as every model is just a simplification of how the joints, the real body work in reality. But here we have these constraints. The left one is the one currently implemented in the model. And if we explore these different regions of joint angles that are inside the range, we see that for a somewhat elevated arm, if we then visualize the rotation range, that this is not as expected, as like this is not rotation of the arm that's possible in that pose for real users. We find a way to fix this. So this should be more plausible. However, this requires that this constraint, which is implemented one of the cores of this shoulder part of the mobile arms model, not only depends on the elevation plane, but also on the elevation angle. So it's like a dynamic constraints or multivariate constraints in two parameters, which is something allowed in OpenSim, but not allowed in Mochoku at the moment. So we might also need to think of how to circumvent it, to which extent more validated, more accurate biomechanical models are needed as basis foundation for our L-based simulations. And of course, similarly, when it's about predicting ergonomics, muscle states, we also need to ensure that these are validated and follow validated laws and dynamics. So we need reliable ergonomic quantities, which could be then aggregated and shown as a ergonomic performance, whatever metric to the HCI designer, which usually has no experience at all in biomechanical simulations or how this whole process works. So this is particularly important for fatigue, which I also quickly want to mention. So we implemented this 3CCR fatigue model, three compartment fatigue model on a muscle level into MyoSuite. So this allows to predict the percentage of active, rested, and fatigue motor units for each muscle during a continuous interaction task. In contrast to, for example, this static default fatigue models in HCI as the one in the XR ergonomics that I've shown. This also allows to account for rests, an important component of interaction design and also of user studies and yeah, is just a more sophisticated model, but especially implementing that on the muscle level also requires some validation of these hyperparameters used to determine how fast a certain muscle type fatigues or can turn into a rested state again. So this requires further validation. But what is possible with that, just to demonstrate this once, for example, here that's applicable to all MyoSuite models. So for example, here with the elbow arm model, we can see how different muscle activations. So here, the task is performed at the same time, change over time. And you can also see now after 8 minutes, it's not possible to do the task anymore. After 2 minutes, it slightly tried to still reach these green target sphere. So we can predict how exhausting it is to do repetitive tasks over larger or smaller time periods, which is also an essential component of most extra games or in general, any interfaces also in the work domain. And yeah, this also gives us clear predictions. So this, for example, shows that for this bend flex movement, it's mainly the biceps muscles which become fatigued, which are affected, and to predict how fast this happens. And we could use this to intervene and create adaptive systems. So validated muscle contraction and fatigue parameters are essential. And what's also on the list is to extend this to other body components also relevant for a lot of interaction tasks. Of course, hand-finger, which would give us way more opportunities to model gesture-based input, but also in mixed reality, where it's about grasping physical objects and using those as representation or interaction tool. And also the neck, torso, and eye movement. Eye gaze is also a very important condition that could be neatly integrated here. So I think the MyoSim and MyoSkeleton efforts of providing these different components are really essential here for our work for biomechanical predictions in UI design. The second problem is the lack of diversity in biomechanical user models. So here the left plot shows the distribution of the arm lengths for, I think it was 10 years ago, US population, both for females and males, which clearly does make a difference here, but both have a quite large range of possible values, of possible arm lengths they can attain. And the red line you can see here is, I think it was the 50% quantile of the male population 20 years ago when this original Holzbauer model of the shoulder and arm was built, which was iterated on and is still at the core of actually all myo-arm, all muscle, all shoulder models used at the moment. So publicly available as a resource that can be used by designers and researchers, we clearly have only this single model. And we were interested in how well does training a policy with this model generalize to changes in the arm length afterwards. And maybe less surprisingly, um, identified that this is not really generalizable. So we were indeed a bit surprised that it only requires changes of 2 centimeters in the arm length to considerably reduce the reward and also increase the task completion time that it needs for, I think here we use the pointing task in mid-air. So to degrade performance and also prediction quality, which requires us to think about how can we integrate or capture this diversity of not only arm lengths but also other muscle parameters such as the maximum voluntary torque, for example, muscle loss, especially for elderly people, might be a relevant parameter to think about, or in general, generate these or customize these models. So vision or goal would be to have a workflow for personalizing these biomechanical models and creating personalized biomechanical predictions or simulations out of that. And finally, the last, for everyone who has worked with RL, kind of obvious problem is the reward function design. So here it's more or less hand-tuned what we came up with in the first approaches for these types of tasks I've shown in the beginning. And as you can see, there is some resemblance or relation between those simulations, but they all seem to be fine-tuned. I think that's the case for most reward functions used across motor control-based RL policies in locomotion, in manipulation, wherever. So we were interested in, given that we envisage a usage of this as a tool for less not at all experienced HCI researchers and designers, can we provide guidelines of how to design an appropriate, reasonable reward function? So what we started with is here this generic formulation of including a task bonus. So that's kind of a sparse, discrete or binary term that where we define for the given task a set of desirable or goal states. They do not necessarily need to lead to early termination, but they somehow tell us what is desirable. And this are given a constant term, these states. All others are given or a constant positive reward, or all other states are given 0 rewards. So that's just a very simple task bonus, which often can also be derived from the scoreboard in VR games, for example. So it's not difficult to come up with this one. But we also included other terms to see how relevant they are. The distance term, like a guidance, because we're mainly focused on reaching tasks, a guidance term in general to get to those states, and an effort terms limiting the highly overactuated nature of the control space. And we tested different models for distance and for effort established in literature. So Euclidean distance, exponential distance penalty, and also all kinds of effort models that have recently been used in reinforcement in the last years. And train and analyze those for across 5 different interaction tasks, resulting in more than 500 policies, and derived some guidelines. So this is what was late-breaking work. We have another full paper on that, which is currently under review. But we were able with coming up with some initial guidelines which clearly need to be adapted to other environments and verified and validated. So, for example, we found that it is essential to integrate or start with this guidance components. Of course, also adapting this task bonus. We came up with some guidelines on that. But on the other hand, the effort term was not really necessary to produce at least some plausible or successful interaction tasks, which was kind of surprising regarding that usually also stabilizes the training process. So yeah, if you're interested in that, feel free to read this late breaking work here. And slide related, as a last comment, we also have the problem of coming up with biased or avoiding biased strategies. So here we see one learned successful performance strategy of the whack-a-mole game, and it looks good from just the statistics. But if you look closely, you see the simulated user has learned to completely ignore all the targets on the left part, which is not actually optimal. Seems more like a local optimum it gets stuck with. So yeah, if things like this can easily appear or evolve during training, how can we ensure that it still produces reliable, or at least state to which extent it produces reliable states and predictions of how users might interact with that. So that's also one of the important questions that needs to be addressed. In this case, we have, as a proof of concept, demonstrated that an adaptive task curriculum, which just assigns higher probability to those tasks during the training that have a lower success rate. So we just focus more on the weaknesses of the model adaptively during training, results in a better balanced strategy or even in total better performance strategy that is able to reach all of those targets. But this might be undesirable from a designer's perspective because we really need to intervene with the game dynamics, which is not always possible or desirable. So in general, we have the problem of how to come up with enough reward, but not introducing a bias towards certain strategies. So opportunities for this are clearly combining this purely reward function RL-based approach with reference data, or also that's what we currently investigate using more sophisticated learning methods. So to summarize, we've seen across all these interaction techniques, they have something in common. They are most based on movement, and biomechanical simulations can help to understand this movement. So I'd like to thank all co-authors. Here is the list of Sim2VR paper, which I spent a lot of focus on this talk. But most of those people were also involved in the other project presented today. So thanks for that great effort. And I'd like to conclude with a slide on the summary of benefits of biomechanical simulations for HCI. From a researcher's perspective, we can gain a better understanding of movement interaction, validate and test existing models, but also analyze different effects in a simulated, but hopefully to a desirable extent, valid simulation platform or environment. From a designer's perspective, we can predict movements, ergonomics, fatigue, or even potential user strategies, loopholes, and as a next step, develop customized and adaptive interfaces that are also more accessible and more usable in a general way. So thanks for your attention, and I'm looking forward to the discussion.
Yeah, thank you, Florian. It's such an extensive and intense work, right? So I will open the audience for question and discussions. People feel free to jump in and ask questions. Yeah. Yeah, I think I will ask my question. So like I think one really interesting thing since we last talked is that now you reintroduce the difference between the reinforcement learning, how the reward function design actually fair and play a major role in this biomechanical simulation users. Like it's completely different. So one thing I was thinking about, like in cognitive psychology literatures, people talk like the reward function is actually something your connection do. Like what your prefrontal cortex does is design the reward function, and then what your reinforcement learning does is controlling the movement. Yeah, I was just curious, like how, like I think you haven't built in like this like cognitive model, like what like the people is actually thinking and stuff yet. Like yeah, I would happy to learn your thoughts on that. Yeah.
Yeah, it's a very good point. So, as you pointed out, it's also the case for though we integrate perception and have these assumptions on optimal feedback control, which somehow are, or at least some define some constraints or boundaries on what we think happens on a cognitive level. This cognitive part is clearly underdeveloped at the moment. So it's mostly focusing on these biomechanical simulations, which is also the reason why it's much easier to apply these simulations to low-level interaction tasks like pointing to a certain position or the choice reaction as a bit more complex task, but still not providing that creative freedom of deciding on your own what to do actually. So you're absolutely right. These cognitive models is something that's missing at the moment and that should be implemented. And there's a lot of different frameworks of how this can be done. and reconciled with reinforcement learning. So I think one thing that might make sense is to think about that difference between external and or extrinsic and intrinsic rewards. I think that's one of the common formulations where we have an external signal of reward. For example, as I mentioned, the scoreboard telling you how well you perform in a given interaction task. But this is not directly used to optimize or decide for a control, but rather brought together with internal objectives, experience history to an internal reward function. So coming up with a good framework or cognitive model that reconciles this and integrates this is definitely a next step needed to increase the applicability or scope of these simulations.
Yeah, just to add on that, like recently, I think there's a lot of robotics was start using large language model to just directly design the reward function and it's doing pretty good. I was just wondering,
Yeah,
maybe like the large language model can be the cognitive model,
yeah,
yeah, something like that.
definitely. So I think that that's possible. I mean, yeah, I would be interested in doing both because we again then have the problem we have a higher controller that is a total black box. We don't know how it comes up with ideas or defines its strategies, and we have the biomechanical model, which yeah, or at least the trained controller from NNs for the biomechanical model, which is also not analytical interpretable. So I think it's always about the scope. For applications in HCI, it was about exploration of the possibilities of a large design space or getting a rough first estimate of how users might perceive a task and interact with that. I think LLMs can definitely help as they can also incorporate like priors or yeah, yeah, just rough estimates of users' perception of affordances and these kind of ideas. But on the other hand, I think we also need a more general, um, more sophisticated but generally applicable framework that might extend beyond RL or at least use more hierarchical RL models to have these different components. So it's also one of the problems at the moment is that we need to retrain um, that we basically train each agent, each simulated user from the scratch. It always needs to learn, which takes around 10, 20 million steps to do the basic motor tasks before it can learn how to control the joystick and then use that joystick to complete the given remote control task, for example. So I think integrating these skills on a lower level and then using them is also an important aspect.
Yep. Um, and anyone else have any question? Yeah, Chun Kun, please ask your question. Yep.
Hi, can you hear me?
Yeah.
Thanks for the talk. It's very interesting, and the visualization is really nice. And I just have a short questions regarding the training the policies. I was just curious, like, have you tried to, because as you just mentioned, you train like each policies from scratch each time? And have you tried to, for example, start with some like pre-trained policies that work on several tasks and then like just fine tune on like individual tasks and compare the performance? Because like I'm just curious,
Yeah. Very good
how's the
question.
process like? Yeah,
So yeah,
thanks.
we tried that a bit. We did not do an extensive analysis of that because I also think there is potential, or I think it's more about finding the properties of these tasks where we train the general, hopefully generalizable first instance policy for it to reuse it later. Because here we noticed even if we, for example, we had these two basic tasks of pointing and choice direction. So if we use pointing and then want to reuse and also fine tune for some more steps on the choice direction task, which has some different cognitive aspects. You need to infer the color and then choose the right button. And also it was physical buttons. So we have different contact dynamics, different physical properties that might already, even though the movement might seem quite the same might already lead to problems where it's more efficient and also results in more reliable policies if we just train from the scratch. So I think it's more about coming up with what is the necessarily low-level skills that we learn independent of the specific task instantiation, and then I foresee large potential of fine-tuning them later.
I see. Thanks.
Hi, thank you for the amazing session. Sorry, I joined the call a bit late. I do have a question with regards to the observation space here. So in order to train the policy when it comes to the observation space, since the goal here is to create something that's more generalized and can be used for any application, is the observation only based on the image, or does it also take into account any information with regard to the application itself? Like, um, for example, the whack-a-mole, does it take into account about the target positions or the hand positions? Are those things considered as well, or is it just the image that's taken?
Yeah, very good question. So um, it is basically the image. So because we wanted to learn the agent to really, or require the agent to rely on this visual data to infer the task goals to some extent. It was clearly an end-to-end approach. That's also why it's hard to observe to which extent these two, because actually it's two tasks in one. We first need to, from the vision, infer the task we want to solve, like so the motor control task we want to solve, like which is the correct color in the choice direction task, and therefore which is the button and then the position I want to point to, and then learn how to control the muscles to pursue this task. That's why I think splitting this up in whatever sense would make sense. But here we trained it end to end and wanted to at least require the agent to rely on that image. So if we would have provided directly the target position, just from the dense reward signal, that's also something we tested and verified. There's not much additional value of this visual information. So this is not required, but you're absolutely right that it currently also limits the generalizability, or maybe not limits the generalizability, but rather requires thinking of a correct rewrite function for each task individually, and also of the observation space. So we need to model each task, decide which is the general information we need to give. So we have that opportunity of incorporating information about the task in the observation state. I think for some of the tasks I've shown, we, for example, included the time relative to the beginning, such that it could learn how whether it's the first movement or whether it has already some failed trials or something. We did not really investigate how important that was. But some information, in addition to what can be visually and somatosensory observed, can help. But we try to keep it to a minimum for now. So it's mainly this combination of vision or perception and then motor control. So another project we currently also try to include auditory feedback, which might also provide important cues in many VR interaction techniques. So we'll be interested in how can we model whether audio cue, to which extent these different cues, audio, vision, whatever, are used or relevant for used by the simulated user and relevant for a successful performance, and in combination with other well-established HCI metrics of usability and aesthetics and whatever, this could also inform the general interaction design, given the large space of possibilities we have in VR specifically.
Perfect. Thank you so much. I do have another question. Most of the biomechanical models that were used for the applications were heavily right hand based. Um, did you perform any kind of ablation study to see the differences between using a bimanual model and just the right model for the same application? Was there any difference?
Also, a very good question. So, yes and no, we did not really train on that. We had some tasks that was bimanual keyboard typing where we used that, or which is kind of a bimanual task itself, but even there we only trained a controller for a single arm, and that was mainly because of the dimensionality of the actuator space. So we did not because this requires additional motor coordination to decide when to, if you in a keyboard typing task, could click the same button in the center of the keyboard with the right or with the left drum to decide when this is done. So again, I think more cognitive models are needed for this level, but in theory, we have these bimanual models, and it's possible to also model interaction with those.
Thank you.
Yeah, thank you for the audience for the awesome discussions, and thank you, Florian. For people who are not able, because that's going to be hosted as a podcast on the YouTube channel. For people who is watching this later, didn't get a chance to ask Florian any question in person, just feel free to shoot him an email anytime, or ping him in the Mouse Week channel. And thank you so much, Florian. It's
Yeah, thank you so much for the invitation.
yeah, very intense. And then we shall stop recording. Okay.